The name of this video is Uniformly Polarized Sphere Part 1. This is one of the most important problems we are going to encounter about the electric materials. We will eventually come back to this problem at the end of this section about the electric materials, when we will attempt to solve the self-consistent problem self-consistently. That is, we will attempt and succeed in taking into account the external field E naught as depolarizing field, something which we are not doing now. So now again, I'm assuming that somebody gives me a sphere, a hard sphere made of the electric material, like a sphere of amber or of glass or of quartz, and somebody gives me a vector field P, capital P, that is a polarization vector, which again is given to me. I'm not trying here to deduce it, to find it from an external polarizing field E naught. We'll come back to that again at the end. So this is our sphere. Let's make it here. So this is the center of the sphere, which is characterized by a radius capital R. This is the center of the sphere. As I already said, somebody gives me a polarization field, a vector field P, capital P, which is again uniform within this sphere. So the field lines of vector P are uniform directed towards the right in this fashion within the sphere. Okay, so this is our vector capital P, which is uniform in this direction, to the right. As always, the first step is to identify a proper suitable coordinate system. In this case, we are going to consider a combination, a hybrid coordinate system. One x-axis, which will be directed as capital P in this fashion. X, this is our x-axis. And in addition to this, so this is the one axis of a three-dimensional Cartesian coordinate system, only one of them. That's all we need in this case, because P is directed only along x, not along y or z. And in addition, we are going to consider a spherical coordinate system where the radial axis r is directed in this fashion, and the center of the sphere coincides with the origin of both the x-axis and the r-axis in the Cartesian and spherical coordinate systems respectively. This angle here, we call it theta, which happens to be exactly the same as this angle here. This is also theta between P, capital P, at the last point on the surface of the sphere with R. Let us assume that within the sphere, the region is capital omega, the surface of the sphere, as always, is capital sigma. Let us call region 2 the region within the sphere, and region 1 is the vacuum outside the sphere. So the sphere is all inside here. There is vacuum outside. In this specific case, n/1, the normal unit vector at any point on capital sigma clearly coincides with UR, the radial unit vector according to the spherical coordinate system. In addition, let us define immediately this quantity here. So from this point to this point, this quantity very important towards the end of this series of videos on the uniformly polarized sphere made of dielectric material. Well, this quantity, we will call it capital X. So small x is as simple as this. There are not these serif here. And capital X, I put these little serifs so that we can clearly distinguish it. Okay? And this capital X, since it's a point, it's the x component of a point on the surface capital sigma of the sphere, is clearly given by r cosine of the angle theta. In this, with respect to this coordinate system, one of these coordinate system with the x, for example, since p goes along x, in this specific case, capital P vector, the polarization vector, is uniform, so it's given by the norm of capital P vector along the ux direction and is uniform. Since it is uniform, we can also immediately find that rho p, the volume polarization charge, is given by minus the divergence of p, capital P vector. However, this is a uniform vector, therefore this is equal to 0, as always in the case of uniform charge, in the case of uniform polarization fields P. Instead, sigma P, which is given by capital P vector dot n, and in fact in this case n is n to 1, towards vacuum as always in our definition. In this case, this simply gives us the norm of capital P vector. It's this vector here dotted with UR, and so the dot product gives us a cosine of theta. This is our distribution in this case, okay? Because again, this comes from UX dotted with UR, which gives us cosine of theta. Great. Note that this sigma p is non-uniform, okay? It's a local distribution at each point on the outer surface of this sphere, and is non-uniform, which is important. Now, a question which I have for you in Piazza is, given such a charge distribution sigma p, this is the question in Piazza, I want you to prove that the total charge Qp is equal to 0 by integration. You need to use, of course, this norm of capital P vector times cosine of theta as your sigma p in this case. And I want to show you that Qp is equal to 0 by integration. Now, we could solve this problem, for example, using the Coulomb's law method. We have seen three methods. We introduced three methods to solve problems related to dielectric materials. Okay, one is the Coulomb's law method. So how would we proceed if we wanted to use the Coulomb's law method? So I'm first introducing the two methods we are not going to use because they are mathematically hard to deal with, and then eventually I will introduce the one we are going to use to solve this problem. So in this case, we could find the electric field E at any observation point R, vector in space, with respect to this origin O, as 1 over 4 pi epsilon naught, the volume integral. Well, in this case, actually, we don't have a rho p, so the only thing we need is actually a surface integral, because the charge is only distributed on the surface, on the external surface of the sphere. So we just need the surface integral on capital sigma of the charge distribution, sigma p, which is nothing but the norm of p vector times the cosine of theta, so it's non-uniform, times the distance r minus r prime, as we defined in one of the previous videos. This is a vector, Coulomb's law, divided by the norm of r minus r prime quantity cube d r prime quantity square, because it's on an area. As it turns out, this is a hard problem to solve mathematically. So we're not going to follow this procedure. You could. It's just Coulomb's law. Okay, so this was the first method. The second method we could use is the Laplace's method. Which we also introduced in a few videos ago. So in this case, as a boundary condition, we have the sigma p is equal to the norm of p vector times the cosine of theta. This is my boundary condition. This is true for each point r, small r, observation point, equal capital R, that is on the external surface of the sphere. Anywhere else in space, since P, capital P is uniform and there is vacuum outside, we just have a Laplace equation equal to 0, and this is true for each r different than capital R, inside and outside the sphere. However, the behavior of this Laplace equation is quite different depending whether I'm in r smaller than capital R or r larger than capital R. Let us focus, for example, to the case where small r is smaller than capital R. That is, we are inside the sphere. So if we focus to this special case, what kind of Laplace equation do you expect to find in this case? Okay, so this is very important, it's a critical step. I will come back to it again, but this is the typical point where people make lots of mistakes, okay? So inside the sphere, what do we have? Capital P is uniform. Remember that capital P is generated by, eventually, an E naught, an external field, which also must be uniform. Otherwise, typically, P would not be uniform, at least for all the cases we are going to study in this course. So E naught, which is the external field polarized in this sphere, is directed as capital P, towards the right, along the x-axis in this specific case. So the external field is directed along the x-axis. Now, what people typically don't understand here is that even though this is a hard sphere, so it has a shape of a sphere, yet the field is only along the x-axis. So the fact that there is a radial axis here should not make a difference. The E naught field is along x only. Regardless of the fact that this has a shape of a sphere, this impact, for example, sigma p on the surface, and that's why this cosine theta comes up. But E naught and p are directed only along the x-axis, though this is a kind of a symmetry in the problem. So when you have a uniform field which is directed only along the x-axis, which is the case inside the sphere, what kind of Laplace equation do you expect in that case? Well, the degree of freedom, which I expect in that case, is 1 and only 1, and is x. Even though this is a sphere, it doesn't matter. The external field doesn't care about the fact that it's a sphere. This will only change again what happens at the boundary of the sphere. But anywhere else, this is an E naught and p, therefore, along the x-axis. So the only degree of freedom is x. And so, the Laplace equation we need to solve inside the sphere, within this Cartesian coordinate system, is the scalar Laplacian of v only function of x equals 0. And this has a trivial solution, which we have seen in Phys 242 multiple times. V of x is the simplest that you can get among all the three cases we've seen, right? It's the same as an infinite plane, is the same kind of solution. And so obviously in this case, Vx has to be alpha x plus beta within the sphere, where beta is an arbitrary constant. Okay? So this is quite interesting because it seems so complicated because we have a sphere, but the uniformity of the external field actually makes it very simple inside. Now, outside is a different story because there we have a sigma p, which is distributed along this capital sigma, which has a spherical shape. There, the spherical comes in. Inside, it does not. Okay? So outside, I'm not going to comment now. Eventually, we're going to solve it with the third method, which is the dipole moment method, the effective dipole moment method. So, but this Laplace method already allows us to understand that the Vx within the sphere has to be only of this type, with a single degree of freedom, which is x. In the next video, what we are going to do is to study the third case, which is again the effective dipole method, which will allow us to find mathematically everywhere in space, very simply, both V and E, the potential and the field, due to this distribution of charge, sigma p, in this specific case. So this, to recap this video, this is part 1. I will keep this figure here, which is the sphere itself with all the coordinate systems x and r. All these charges we know that are the charges we need to consider in this problem. The first two methods, we are not going to go into more details. Also, this one, incidentally, is not easy. It's also pretty hard to solve it, so we're not going to use it. But it already gave us a glimpse of what is going to happen inside the sphere, which is very important down here. Typical problem that many students do, and many students have. The fact it's only along x-axis. Outside, of course, is not the case. But again, this we are going to study in the third case, in the third method, which is the effective dipole method. Remember, one of the three methods we introduced at the beginning of this series of videos. That's it.